So suppose you have found a finite difference approximation of your Poisson equation. It will remind very much of formula 617, except for the fact that your right hand side should have k squared times fij instead of just 0, but the left hand side will be more or less just similar. So the question now is, how will you implement this in a computer, or how would you try to solve all of these equations at once? So if you look at 617 in the book, formula 617 on the beginning of page 189, you will notice that the equation that is written in 617, it varies in index I and in index j. And the interesting thing here is that actually what you have is n times m equations. So what we're going to do when we try to solve Poisson's equation numerically is we have to solve n times m equations at once. So if I ask you, is this an implicit or explicit method, then it's quite surely an implicit method, because we solve the problem by solving all of these equations at once. And the thing here is, if we, for example, consider the stencil for this problem, then what we have is, along the unit square, then we know all the values that are on the boundary. So all of these values here will be shaded dots, while the values that we don't know are all the other values that lie in the grid inside of, well, this is a very ugly grid, but you get my meaning, you get my point. We need to use these values out here to find all the values of u inside here. And for each dot in here, there is an equation governing the value of this dot, we found this equation using different using finite difference approximations earlier. So you will arrive at something that looks like 617. And now the trick is, well, how do you write up all of these n times m equations in a way such that you can solve them in some kind of matrix system? So let us look at how these n times m equations are supposed to look. I'll just write down what I see in the book. That rhymed. Minus lambda squared times ui plus 1 comma j plus 1 plus lambda squared uij minus lambda squared ui minus 1 comma j minus uij comma j plus 1 minus ui comma j minus 1 equal, well, not 0, because we're not dealing with Laplace's equation, we're dealing with Poisson's equation. And because I won't tell you what's over on this side, I'll just call it question mark. So, how do we write this up in a matrix equation, where we know that the i's are supposed to go from 1 to n and the j's are supposed to go from 1 to m? Well, in the earlier sections in the book, it was easy enough, because then we said, let's just solve these equations one matrix at a time, in the sense that we considered everything that had something to do with j and everything that had something to do with j plus 1, and then we just threw j plus 1 over on the other side. The problem here is, because of how our stencil looks, we can't just do that, because we also have something with j minus 1. So we essentially, we have to solve all n times m equations in one go. So we're not able to do some kind of update matrix equation where we let where we start by solving one matrix for a fixed j and then a next matrix for the next j and so on. Here we have to do it all at once. And that is why we have to find a way of indexing these such that we are able to solve all n times m's equations at once. Now, if we want to solve n times m equations at once, we have to have a matrix system that allows for n times m equations. So what we want is we want a matrix system of the form A times U equals B, where this is a n times m times n times m matrix. So A will have n times m rows and n times m columns, and where U will be n times m long and have one column, and B also will be n times m long and have one column. So how are we supposed to index these if we want things to, well, go our way? One way to do that is using the lexicographic notation, lexicographic ordering which they use in the book. So to understand the lexicographic ordering, I recommend you look at section 621.